In this video, we will consider the application of student t distribution in testing of hypothesis. The student t distribution is applied to test the mean of a normal population has a specified value and also for testing equality of means of two populations, and then t-test for paired samples or dependent samples. In large sample test, we have found that the mean of a population has a specified value. Here we consider a sample x1, x2, etc. xn drawn from the population with the mean mu and standard deviation sigma. And the statistic t equals x bar minus mu root n by sigma follows n01. For the construction of this statistic, we make use of central limit theorem, and therefore the distribution of the population is not necessary in that case. And note that this standard deviation sigma, if known, then only the statistic t equals x bar minus mu 0 root n by sigma can be applied for testing mean of a population has a specified value. And if at all this sigma is not given, we can write yes in the place of sigma and proceed with the statistic, same statistic following n01. And when sigma is unknown and sample is small in size, that statistic is inapplicable. In that situation, we make use of the statistic following student t distribution. So here we have a sample taken from a population following normal distribution, and x1, x2, etc. xn represent the variables drawn to the sample. We take x bar as the sample mean and s as the standard deviation of the sample. In this sampling distribution, student t distribution, we found that this a sample of size n taken from a population following normal distribution. We have the result t equals x bar minus mu root n minus 1 by s follows t distribution with n minus 1 degrees of freedom. This statistic is constructed using the relation t equals z by root of chi square by n follows t distribution with n degrees of freedom. Here this numerator z is taken as x bar minus mu divided by sigma by root n follows n01, that is standard normal distribution, and that distribution is obtained using the sampling distribution of mean of a sample taken from normally distributed population, and that's why we have the sample drawn from normal population, and the sample mean x bar follows n mu sigma square by n. Further, we have chi-square equal to n square by sigma square follows chi-square distribution with n minus 1 degrees of freedom, where s square is the variance of a sample taken from normally distributed population. Therefore, for the application of this statistic, it is mandatory that the population following normal population, the sample drawn from a normal population. That's why this title is exclusively for test for mean of a normal population, and therefore the sample small in size and sigma unknown. The test criteria based upon t distribution is applicable only for populations following normal distribution. So we have the statistic x bar minus mu root n minus 1 by s that follows t distribution with n minus 1 degrees of freedom. Note that here no presence of standard deviation of the population. It is given here the standard deviation of the sample. Standard deviation of sample is given to us. So the H0 true, the statistic is x bar minus mu 0 root n minus 1 by s. This is the statistic used for testing mean of a normal population has a specified value when the population standard deviation sigma unknown and sample small in size. Now we can construct the critical region corresponding to various alternative hypotheses. First we consider the right-sided test, that is H0 mu equal to mu 0 against H1 mu greater than mu 0. Here we take the critical region as T greater than T alpha, where T alpha is obtained from tables of student t distribution for n minus 1 degrees of freedom, and it satisfies the probability equation T greater than T alpha when H0 true equals alpha. That is, from the tables of student t distribution we get the table value T alpha corresponding to the degrees of freedom n minus 1 and probability alpha. Here you can note that the probabilities are given in the top of the columns in two rows. What is, the upper row gives the two-sided values and the lower row gives the one-sided values, that is the bold digits for two-sided and the regular digits for one-sided values. So if degrees of freedom is some 7, then 0.05 in the lower row, that is the coincidence, say 1.895, it represents the table value for a one-sided test. And the same degrees of freedom and probability 0.05 in the upper row gives the two-sided test table value, that is 2.365. So based upon this principle, we refer the table value from students' t distribution tables, and the null hypothesis is rejected if t greater than t alpha when the test is right-sided. That is, the critical region for a right-sided test is t greater than t alpha, and t alpha from tables of students' t distribution such that probability of t greater than t alpha when h0 true is equal to alpha. Then the shape is given in the graph of the student's t distribution. Here, this shaded section represents the critical region and its area is alpha. Therefore, when t equals 0, that is when x bar and mu 0 coincide each other, there is perfect agreement between the sample mean and the suspected value of the population mean. But we are ready to accept the population mean as mu 0 itself till we reach at T alpha, that is between 0 and T alpha. If it goes beyond T alpha, we reject the hypothesis, that is at 0, mu equal to mu 0 rejected if T greater than T alpha. So T alpha to infinity area is point alpha. If alpha is 0.05, the area will be 0.05. We note that the tail sector areas are tabulated in tables of students' T table. It is unlike the tables of standard normal distribution or the area starting from 0 to some set. Here this area from T alpha to infinity is tabulated. That's about the student's t test for mean of a population has a specified value when the test is right-sided. Likewise, when the test is left-sided, we take h0 mu equal to mu 0 and h1 mu less than mu 0. Then the critical region is t less than minus t alpha. That is the just equivalent sector coming in the left side of the frequency curve of students' t distribution, and this left-sided tail section, the shaded area, is alpha. So we reject the null hypothesis if t less than minus t alpha, and minus t alpha or the t alpha can be obtained from tables of students' t distribution, and alpha one-sided, that is significance level completely assigned to one side only. Therefore, in the tables we refer the 0.05, the level of significance in the lower row, that is the row representing one side areas. Now the next is the student's t distribution testing for mean has a specified value when the test is two-sided, that is h0 mu equal to mu 0 and h1 mu not equal to mu 0, that is two-sided test. Here the total significance level alpha will be shared into left and right sides. Therefore, we have T alpha by 2 from tables of students T distribution, and the rejection region is either T less than or equal to minus T alpha by 2 or T greater than or equal to T alpha by 2, or combining those two segments, we have modulus T less than or equal to modulus T greater than or equal to T alpha by 2, not less than or equal to. Therefore, the rejection region is modulus T greater than or equal to T alpha by 2. Here, the lower side, left side critical region is the shaded section, that is less than minus T alpha by 2. Here comes the point of minus T alpha by 2, minus T alpha by 2 less, and the right side is plus T alpha by 2 above. And we can note that the table value T alpha by 2 can be obtained from tables of students' t distribution. For example, if degrees of freedom is 7 and this alpha 0.05, the table value will be 2.365. There we have to take the zero point zero 0.05 in the upper row, because the upper row probabilities represent two-sided areas. So even though we have zero point zero 0.05 in the upper row and lower row, there is differences in the areas occupied. The zero point zero 0.05 upper row represents the total area considering left and right side, that is two-sided, and zero point zero 0.05 in the lower row represents the area occupied only in one side. Therefore, the test is right-sided or left-sided. You have to refer zero point zero 0.05 from the lower row and zero point zero 0.05 from the upper row when the test is two-sided. Therefore, that's about the critical region corresponding to various alternate hypotheses of this testing at 0 mu equal to mu 0. Now we have then the second application of T distribution, that is T distribution for equality of means of two normal populations. Here also this test is applicable when the population standard deviation sigma 1, sigma 2 unknown and samples small in size. Also note that this is only for populations following normal distribution. So again in the sampling distribution of that is of student state distribution, we have the statistic x1 bar minus x2 bar minus mu1 minus mu2 root of n1 s1 square plus n2 s2 square by n1 plus n2 minus 2 into 1 by n1 plus 1 by n2 follows T distribution with n1 plus n2 minus 2 degrees of freedom. We make use of this result for uh, the statistic to test H0 mu1 equal to mu2. So the null hypothesis is H0 mu1 equal to mu2, where mu1 and mu2 are the means of the two normal populations. And when H0 true, that mu1 minus mu2 will disappear. Therefore, the test statistic is x1 bar minus x2 bar divided by root of n1 s1 square plus n2 s2 square divided by n1 plus n2 minus 2 into 1 by n1 plus 1 by n2, and this statistic follows T distribution with n1 plus n2 minus 2 degrees of freedom. Now, the critical regions corresponding to various alternative hypotheses are just discussed in the case of uh, population mean has a specified value using T distribution. That is, when the test is right-sided, mu1 greater than mu2, then the critical region is T greater than T alpha. When the test is left-sided, mu1 less than mu2, then the critical region is T less than minus T alpha. And if the test is two-sided, the critical region will be deployed in the left and right sides. The sections are T less than or equal to minus T alpha by 2 or T greater than or equal to T alpha by 2. That's about the test for equality of means of two normal populations based upon T distribution.